All right, I'm sharing screen. Can you see my slides?
Yep.
Yeah.
Yes.
All right. Well, thank you very much, Renzo, for inviting me and giving me a chance to show some of our most recent work here. Yes, and apologies that my bad. Somehow I had it on the calendar for next Wednesday, not this Wednesday, but it's fine. It is what it is. So the bulk of the talk today will be looking at some of our recent work, which looks at depth-dependent task modulation in ventral temporal lobe with ultra-high-field fMRI. Just a brief outline. I'm going to start with a very small background and very briefly touching upon mesoscale cortical organization. And, then I'm going to provide some of the motivation and rationale for the current study. Briefly talk about Nordic denoising to then focus on the current study and some of the future direction, which will mainly include RTEM5 fMRI data. So while I spent the last 9 years, a long time at CMRR, working in close collaboration with Issa, Yaku, and Kamil, Steen, and Mehmet, and focusing on obviously image acquisition and acquisition parameter and so forth. I am a cognitive neuroscientist by formation, and like many of us, if not all of us, I see fMRI as a key tool to study the human brain non-invasively. And the thing I'm interested in most is visual perception, and specifically how we come to form a coherent percept of the world around us. And I think that fruitful path to study, some crucial processes in understanding how we come to form an individualized perception of the world around us, the interplay between feedback and feed-forward processes. And a fruitful path in studying this interaction within these different processing paths is looking at mesoscopic scale organization in humans. And obviously, we all know that with highly efficient accelerated acquisition protocols, we can acquire images with sub-millimeter precision, and that this nominal resolution allows, at least in principle, to study human neurofunctional organization, the mesoscale level, targeting some of the most fundamental units of neural computation, like layers and columns. So very briefly, these are just some brief pictures. We've known for over 100 years that the neocortex is divided in at least 6 layers, but obviously even more partition. And each layer is characterized by different cell type and concentration, as shown in this histological sections of macaque visual cortex. This Neal staining, you can clearly see the different layers. And that the response properties across these layers, especially in early sensory cortices are organized in a columnar fashion, meaning that layers that are arranged perpendicular to one another exhibit comparable, if not identical, response properties. Some of these organizing principles, very well-known and examples of organizing principles are, for example, ocular dominance columns or orientation columns. This is an example of, again, macaque monkey ocular dominance columns in visual cortex. So many decades of invasive electrophysiological research in animals has shown us that cortical layers are underpinned by a very specific connectivity. So these are oversimplified models, but what we know is that feed-forward primarily terminate in the middle layers, while feedback in inner and outer layers. And therefore, we can leverage this spatially constrained signal to study feed-forward and feedback processes at the cortical depth levels in humans using ultra-high resolution, ultra-high field fMRI. And here are some of the examples of these some of the studies. There's Issa's paper 2007, where they show both orientation and ocular dominance columns. There's one of Federico's paper, Federico De Martino, showing tonotopic maps are organized in a columnar fashion in primary auditory cortex. That's the paper that we put out with Lars Mukli in 2015, where we show that contextual feedback primarily terminates in the outer layers of V1. And then there's the Lawrence et al. Paper that shows that bottom-up amplitude is largest in the middle layers. And then there's many of Renzo's paper, this one, the earliest one, the 2017 neuron paper, where he used Bezo to show, and different tapping condition to show the ability to detect a double peak across the layers. So many groups around the world have started exploiting this sub-millimeter fMRI to tackle this mesoscopic scale organization in humans. Most human mesoscale studies typically utilize 0.5, in fact, to be precise, 0.512 microliter voxels, which corresponds to 0.8 isotropy voxels. However, even at this resolution, images tends to be limited in SNR. We know that thermal noise is dominant at these resolutions. And while many studies have been successful, this resolution may only be marginally adequate to study human mesoscopic scale organization. If we think, for example, that we have at least 6 layers across the cortical ribbons, and the cortical ribbon spans anything between 1.5 and 4.5 millimeters, it becomes evident that 0.8 may not be enough to capture subtle modulations across layers. As a consequence, most of these studies focus on early sensory cortices where species similarity exists, allowing validation of results against animal models taken as ground truth. Where SNR is highest, like for example V1, V2, V3, where cortex is thickest, like M1, facilitating, for example, cortical depth segmentation, and employing low-level stimuli with, for example, block design paradigm, mostly, again, all this to maximize the SNR and facilitate our job. However, in my mind, and I guess it's kind of like shared amongst most of us, to fully exploit the advantages conferred by fMRI and study, we need to be able to study processes that are unique to humans. And to do so, we need to be able to move beyond early sensory cortices, achieve higher resolution to better characterize achieve higher resolution to characterize better laminar response profiles. So to this end here, we attempt to characterize task modulation to identical images across cortical depths using socially relevant stimuli like faces. So we try to move beyond early visual cortices. So we're still looking at V1, but we expand our field of view to include higher level areas, like, for example, the fusiform face area, which is located in the ventral temporal lobe as the face preferential areas. And we also push our resolution from 0.8 isotropic millimeter voxels to 0.7, which doesn't sound like a lot. But if we think in voxel volume, this represents over a 33% decrease in voxel volume. And we know that voxel volume is ultimately what determines our SNR. So it is quite a significant increase, and certainly a step towards the higher resolution that we want to acquire. So as I said here, we're moving away from early visual cortices, imaging areas that are traditionally difficult to image. We're increasing our field of view, we're increasing our resolution, and therefore we're going to be faced with large amounts of noise, especially thermal noise. And so to deal with this, we use Nordic denoising, which is a denoising algorithm that we recently developed to suppress thermal noise. Most of you are familiar with Nordic, so and all the work is published, and so I'll just give a very brief outlook on this. As mentioned, thermal noise is the dominant noise source in sub-millimeter fMRI, and so to deal with this thermal noise, we developed a local low rank approach, Nordic PCA, so a PCA approach that removes those components that are undistinguishable from Gaussian-like distribution. This based on the assumption that thermal noise, especially in complex space, has a Gaussian distribution. So obviously, we wanted to validate Nordic and determine the impact of Nordic on our functional responses. And to do that, we turn to the retinotopic properties of V1, which provide some sort of like ground truth as to the spatial extent of activation expected by, for example, low-level stimuli in this case. So yeah, the stimuli that we use is checkerboards, flickering checkerboards, two conditions, a target and a surround condition. And one first thing that we looked at were the T-maps to the contrast target larger than surround. And so T-maps can be loosely conceptualized as percent signal change over the model standard error. And here's an example of these maps for a subject on an inflated cortical representation. So this is the occipital cortex, this is the calcarine sulcus here. And in red, we see the activation listed by the target, and in blue, that by the surround for one Nordic run. And then we can compare this activation to one standard run and to a number of concatenated runs of standard data. And so what we see is that we need several concatenated runs of standard data to approach the extent and quality of activation achievable with a single Nordic run. We then look at percent signal change responses. So we're looking at T-maps and computed the differences between the two to assess the impact of Nordic on response amplitude. And in this case, with block design in V1, we did not see any meaningful differences in percent signal change, leading us to conclude that, specifically in this case, Nordic leaves both percent signal change largely unaltered. And so looking at the previous image, the previous result, we have these larger T values, same percent signal change as T values can be thought of signal over error. What we are doing is removing the noise while leaving the signal largely intact. We also observe an increase in the precision of single responses of single blocks. So in an ideal world, in an ideal noise-free world, where we're showing identical stimuli, low-level stimuli, we should observe identical responses. Obviously, it's not the case because the noise increases the variance of your responses. But if we're doing a good job of removing this noise, and we're observing now and we're quantifying the variance across these single block responses, we should see a decrease in this variance, and that's exactly what we see here. So each single dot represents the voxels within the retinotopic representation of the target, and this what I'm plotting is the standard deviation to the single block estimates for Nordic in blue and standard in red. And we can see that these are significantly smaller for Nordic than standard, indicating that the precision of this response estimate is higher for Nordic than standard. So another probably more elegant and also more convincing way of looking at the precision of Nordic versus standard data is looking at model cross-validation. So very, very simple model cross-validation. We can estimate our parameters on one run. So we optimize, we compute, we solve our GLM for one run, estimate the parameters on a specific run, and then we see how well these predict an unseen run. And so here's an example of a single voxel time course for two subjects, for Nordic in blue and standard data in red. And this is the lighter jittery line, and then the darker line is the model multiplied by the parameters estimated on a separate run. And then to quantify how well our data predict unseen runs, we can compute cross-validated R-square coefficient determination, and that's what we're doing here. And then we can compute stats across all the possible cross-validation folds. Then these are summarized here in these bar plots, and we can see that the cross-validated variance explained by Nordic is significantly larger than that by standard data. And then if we look at the spatial distribution of these variance explained, cross-validated variance explained, we see that it's not random, but is spatially localized in meaningful portion of the cortex, and in this case in the retinotopic representation of the target. So again, leading us to believe that with Nordic we can have higher precision of response estimates. And the last point, which to us is one of the most important points, we wanted to make sure that Nordic does not alter the functional precisions of our maps. Obviously, we're literally jumping through hoops to get higher and higher spatial resolution data. And if we had to trade these gains in resolution to deal with thermal noise, we'd be shooting ourselves in the foot. We know that there are very efficient ways of dealing with thermal noise that do lead to significant blurring in our spatial precision. Smoothing is one such example. And so we want to make sure that there's no actual smoothing introduced by Nordic. So to do that, we computed point spread, functional point spread measurement. We turned again to the retinotopic properties of V1. And we computed the target larger than surround contrast, like here. So here, what I'm showing here in the insert is just a flattened representation of the visual cortex. In red, we have the activation to target, and in blue, the surround. We look at where this contrast is 0, and this is our medial most empirical border of the target condition. And then what we can do, we can superimpose this empirically derived border to the activation of the target only. And the fashion in which the activation decreases as a distance from this empirical border will provide information as to the spatial precision of our measurements. So to quantify this, we do something very simple, like Amir did in the Schmuel in 2007 paper, where we have a very simple point spread function, which is nothing else than a stepwise function representing our infinite point spread convolved with a Gaussian kernel. the full width half max, of which is one of the parameters that we estimate, and is the parameter that's going to tell us how precise our measurements are. And so we did this for Nordic and standard data, and we didn't observe any meaningful differences in this functional point spread measure, leading us to conclude that Nordic denoise does not alter the functional precision, does not meaningfully alter the functional precision of our images. So after we made sure that Nordic is not doing anything bad to our data, and where we can use it to remove thermal noise and do maybe some cool neuroscience. So this leads me to today's study. So the motivation for today's study is a paper that we published in 2021 in NeuroImage. In this case, we use supramillimeter resolution, so it's 1.6 millimeter voxels and a fast event-related design using faces with different level of visibility. So we manipulated the phase coherence of the images. And what we showed is then the fusiform face area, both right and left FFA, we can induce significant task modulation to identical visual stimuli. And so we wanted to go and investigate this effect at the cortical depth, dependent or laminar level. And so to do that, again, we use a comparable paradigm where we have different faces with different visibility, ranging from 0 to 40% in steps of 10 of phase coherence. And we switched to a block design from a fast event-related design. This is because we really want to make the most of any little bit of SNR that we have out there. So we know that standard block design elicits larger response samples. So we turn to block design like this, 12 seconds on, 12 seconds off. In the on periods, we had faces presented by 600 milliseconds, followed by 600 milliseconds blank screen. And participants were instructed to respond to each stimulus. And they were instructed to perform one of two tasks. Either a face detection task, indicating whether perceived or not a face, or a fixation detection task, indicating when the fixation turned red. So for each task, we acquire 6 runs, and each runs at 8 single blocks, leading to 48 single blocks per subject per task. So tell me a bit about the methodological details. So this was 70 acquisition using 32-channel NOVA coil, single channel, 0.7 isotropic voxel, this Gray and echo data, with a TR of about 2 seconds. So as I said, we pushed the resolution significantly, achieving over a 30% decrease in our voxel volume, while also increasing our field of view. This is an example of data as they come out the scanner, a sagittal view of our data. So we got both the one here in the occipital cortex as FFA, which is more or less located in this portion here. And we can see the high level of thermal noise here. The images don't look bad. This is a single image API, but we can see the speckly noise up here. So to deal with this thermal noise, we use Nordic to reduce the amount of thermal noise. And here's an example of the same single image API after Nordic, and we can see that all the speckly noise is gone, and the fine grain details, the important fine grain details are preserved. For example, the gray white matter contrast here is very clearly identifiable. Again, to minimize blurring and preserve our spatial precision, we remain in functional distorted spaces. So instead of using our reverse phase encode to correct for distortion in our API spaces, we compute our displacement maps and use that to distort the anatomical, and then the anatomical data, and match the distortion that we have in our API. And that saved an interpolation step, preserving, avoiding inducing further blurring into the data. So here's an example of half of the data. This is the activation, the average activation to the face task for a specific subject, just to highlight that even with a very large T threshold of 5, this corresponds to P00001 FDR corrected or something like that, we still have meaningful activation, which is very well aligned. This was work of Logan Dowdell, who spent a very long time doing making sure that co-registration across modality was optimal, as well as the cortical segmentation. And we can see clear activation even at this high threshold, both in V1, unsurprising, and as well as the anterior portion of the FFA here. So we proceeded to perform cortical depth segmentation using an equivolume approach, and we used Laney, developed by Renzo and Farouk. Here's an example of the cortical depths in FFA here and V1. We actually also looked at OFA. We use an independent phase localizer to identify phase preferential area. This is the standard localizer by Callinically Spector. And then we use a probabilistic map, specifically the Benson Atlas, as well as the first block of each run to identify the retinotopic representation of the stimuli in V1. Obviously, having used the first block as localizer, these were excluded from further analysis. And here's an example of our layer segmentation for a specific subject. On the left, on the mini PI, and on the right, on the co-register T1. This is an MP2 range. And this just to highlight the quality of both co-registration as well as layer segmentation. And again, it was performed by Logan. And he spent a very, very long time trying to maximize and optimize this. And here is an example of single runtime courses for all the layers and all the areas. These are raw time courses, so it's just like after pre-processing. And you can see this is just to highlight the quality of the data, the quality of the time courses, where you can identify each single block. They all exhibit the response properties expected by this paradigm, regardless of the task. So the two tasks here are shown. Solid line is the phase detection task, and the dotted line is the fixation task. The different colors are our three cortical depths. We can appreciate the typical ramping profile for observable Fourier echo data. And we can see that even during fixation task in the FFA, where it should be more or less dormant or less active, we can clearly distinguish our single blocks. So we proceeded to perform single block modeling estimates, leading to 8% signal change betas per run. As I said, we discarded the first one as it was used for a localizer. And then we went on to quantify the task-related modulation by performing the ratio between the activity elicited by the phase task over that elicited by the fixation task. And so here an example for a given subject superimposed on our MP2 range, on our T1. So here we got on the bottom right-hand quadrant, we got our cortical depth segmentation. Red is outer layers, and green is inner, so closer to the white matter. And here on the top row, we got the activity elicited by the phase task and the fixation task. And here at the bottom left, we have the ratio between these two. And we can see that this ratio, so yellow means warm colors means higher ratio, and blue is cooler color is lower ratio. We can see that for this specific subject in V1, this ratio is largest in the inner layer, so closer to the white matter. And then if you look at the FFA for this same subject, again, here we go the insert of our cortical depth segmentation, inner green, outer red, percent signal change for phase and fixation, and the ratio between the two. And here we observe the opposite result. So the ratio between tasks is larger in the outer layers of the FFA compared to the inner layers. So the main results that we observe in this one subject, we see higher activation during phase 10 fixation task in both FFA and V1. This is not surprising. We have seen this before. Task modulations tend to be larger in FFA than V1. In this case, we go up to a threefold increase, while only a 13% increase in V1 for the phase relative to fixation task. Again, not surprising. But the interesting finding here is that these task modulations are most prominent in the outer depths of FFA and the inner depths of V1. So we repeated this analysis for all of our subjects, shown here. I know there's a lot of information, but we replicated the same results for all our subjects, where we observe this task modulation as measured by this metric ratio to be largest in the inner depths of V1 and outer depths of FFA. All right, so to quantify these results, we carried out statistics across our 42 single trials. Specifically, we computed 95% bootstrap confidence interval on the difference across the depth ratios, and we Bonferroni corrected it for multiple comparison correction. And here's an example for one subject. So average all the voxels within a layer. Here on the x-axis, we got our layers or cortical depth going from inner to outer. And in the different color, we got the two different tasks. So fixation task is in red and phase task is in blue. This is the percent signal change responses on the left, and we can appreciate the typical ramping profile of gradient echo data where amplitude increases as we approach the PL surface. And then on the right-hand side, we see the ratio between these two metrics computed at the single block level. And we can see that this was largest in the inner compared to outer depth. And then if we perform the same type of analysis for the FFA, now we'll see the opposite results, where this ratio between tasks is larger in the outer compared to the inner depths, in spite of observing this ramping profile for both tasks at the percent cell change level. This was significantly different. Inner layer of V1 was significantly larger than outer layers, and the opposite was true for the FFA at the single subject level. And so we repeated this analysis for all of our subjects using our bootstrap method to derive our null distribution, our sample distribution as well, and multiple comparison correction. And we report significant results for all our subjects, all showing significantly larger ratio in the inner depths of V1 and the outer depths of FFA. So this is looking at our amplitude analysis. Then we perform functional connectivity analysis, this time independently per task. I'm going to focus on FFA and V1. And so the results of our functional connectivity analysis is going to be a 6x6 matrix, where each cell shows the connectivity between a specific layer and a specific area. We perform dissimilarity matrices, so this 1 minus Pearson's correlation. All we did is just compute the Pearson's correlation between our time courses for one task within a task across all possible layer combinations. And we did the same thing for the other task. So again, these are the similarity matrices. So here, warmer color means lower connectivity, and cooler color means higher connectivity. So even just by visually inspecting these two matrices, we can clearly see that the connectivity in the phase task is significantly larger than in the fixation tasks, especially in this 6x6 matrix here on the off diagonal, which is the one that we're interested in the most, because it's summarizing how V1 talks to FFA, the connectivity between V1 and FFA. So larger connectivity in the phase than the fixation task, maybe indicating that in the phase task, there's more crosstalk between these two areas, which would make sense. And this was, again, significantly different between phase and fixation task, multiple comparison correct, both correct to the PO1. And then we can perform a single subtraction between the two, and then look at t-values or effect sizes, which get to the effect sizes, just to see where this increase in connectivity was largest. And what we observed is that the largest increase in connectivity at the descriptive level was in the inner layers of V1 and outer layers of FFA, and the t-values were even larger for the specific layer pairings. So maybe a simpler way, at least for me, to summarize the result is by computing multidimensional scaling, which is a dimensional reductionality technique, which allows you to replot your data, in this case, our connectivity data, according to the first few eigenvectors, which explain X amount of your variance in your data. So that's what I'm doing here. I'm computing our classic multidimensional scaling for these two connectivity matrices for our phase perception and fixation tasks. And I'm replotting our data in this two-dimensional space where our dimensions are first and second eigenvectors. In this new space, the distance between the point symbolizes the strength of connectivity. The further away they are, the more disconnected they are. The closer they are located, the more connected, the higher is the connectivity between regions. Each single point represents a specific layer of FFA and V1. For a specific subject and run. So I'm showing again single subject and single run at in this graph. So the main results that we can observe is obviously the cloud of point is a lot more sparsely distributed for the fixation and for the phase perception, indicating again that there's a larger connectivity during the phase than the fixation task. And most importantly, to me, the most interesting result is if we look at the gray and these dark blue dots, which represent the inner layers of V1 and the outer layers of FFA, that's where we see the largest shift. These gray dots get a lot closer to these blue dots down here. Again, describing the increasing connectivity between outer layers of FFA and inner layers of V1. So taking together these results, we've got our amplitude results, our ratio results, which indicate that our task modulation are most pronounced in inner layers of V1 and outer layers of FFA. And then we've got our functional connectivity computed independently per task, which shows that connectivity increases during the phase detection task, during the phase perception task compared to the fixation task, specifically for the inner layers in V1 and outer layers in FFA. And so these data are consistent with the idea of apical dendritic amplification as a key mechanism for conscious perception. So one potential putative mechanism could be that this apical amplification originates in the outer layers of the FFA and is obviously transmitted columnarly down to the inner layers and then fed into the inner layers of V1, which is consistent with the electrophysiological report of feedback exchange between outer and inner depths. So we are very excited about the results, and we think it's all really coming nicely together with different analyses to shed lights upon this feedback and feed-forward interaction during phase perception tasks. So conclusion for today's study, I hope that we demonstrate the feasibility of imaging cortical depths beyond primary sensory cortices, including, during complex behavior such as phase perception. We imaged areas of different complexity across the visual hierarchy. So we start from V1, we looked at OFA. I didn't show you OFA results here because we don't see any meaningful results. And then culminating in the FFA as a higher level order, in our case at least, the higher we could achieve in the specific experiment. We observed that top-down task-related modulation are most prominent in the outer depths of FFA and inner depths of V1. And that these findings are consistent with the idea of electrophysiological reports of feedback exchange between superficial and deep layers, and with the idea of apical dendritic amplification as a key mechanism for conscious perception. And so we believe that obviously this works is only like one step, but it presents a very promising step towards characterizing cortical depth functional profile for complex human-specific cognitive processes. Just very briefly, I just want to show you a little bit of what we've been doing at TEM5. Obviously, in our quest for resolution and SNR, the easiest thing is to go to higher magnet. We know that SNR scale linearly with magnet field strength. So at TEM5, we should have over a 30% increase in SNR. And then we can use this SNR either to acquire comparable images with comparable resolution, but better quality, or to push the resolution even further. So this is an example of 0.8 isotropic voxels, 3D API with the volume acquisition time of about just under 4 seconds. These are single image API. There's no Nordic. That's exactly how they come out of the scanner. We use 80-channel coil developed by Matchbox to acquire this data. I just want to highlight the quality of these images. Again, single image API, no Nordic, just as they come out of the scanner. If we zoom in to these images, we can see really fine-grained structural details, even in midbrain, like the red nucleus here, for example, in the middle panel. And then we can start doing some interesting neuroscience. So here as our phase paradigm, we can move away from like gabors and gratings and start looking at the higher level stimuli. And this is an example of a very comparable paradigm to what I showed with the phase perception task. But it's only 25 minutes of data. And even with only 25 minutes of data, we can achieve meaningful activation, even at this resolution, which is not super high, but the coverage is quite meaningful. And then if we look at single voxel time courses, it's just like random single voxel time courses selected in visual cortex. We can see that even a single voxel without Nordic, these look really, really nice, exhibiting all the expected response properties. So red is the stimulation blocks where phases were presented, and gray are the fixation blocks. And you can see clear HRFs, even at the single voxel level without Nordic at 0.8. So as I said, so this is an example of how we can exploit RSNR to get better maps or comparable maps in shorter acquisition time. But we can also use this added SNR and 3D back in to acquire higher resolution data. And so this is an example of something that we've been relatively, I'm not going to say routinely, because it's still not routinely, we've been able to acquire in several subjects, so a 0.4 isotropic voxel, which equates to a voxel volume of 0.06 microliters, approaching the brain-initiated, well, towards the brain-initiated goals, the brain-initiated 2.0 goals of approaching 0.1 microliter. And so here's an example of this 0.4 isotropic voxels at 10.5 on the top, and then everything else being equal as 7, well, as equal as possible, obviously 7 Tesla. Again, here we turn back to our gratings because we wanted our retinotopic properties to serve as a ground truth for validating our activation. And we do expect, based on retinotopic location, activation inside this white ellipsis that I drew on the image APIs, and we can see that we clearly see meaningful activation at 10.5 but not at 7T due to the low SNR, obviously, this lower field strength. I should say that both of them here, they're Nordic denoised, and I'm showing single image APIs at this resolution. And here an example of voxel time courses, again, executing all the response characteristics we expect for target preferential voxels. So target here in dark blue and surround are in cyan, and we can see that this voxel responds only during target condition, not surround conditions. As I said, not quite routinely, but we've been able to acquire data across several subjects. This is an example of 3 different subjects. This is only 20 minutes of data. It is a slow block design, so SNR is, relatively high, but still, we're still looking at 0.4 isotropic voxel with 20 minutes of data, single image API. So things are looking quite good and quite promising. We're quite pleased with the activation achievable, the functional mapping achievable with this resolution. And then this is the last data set I'm going to show today very quickly. These are the highest resolution that we have been able to achieve with Green-Echo API. So it's 0.35 isotropic voxel. This shows the coverage, single image API again, after Nordic denoising. So you can see that even at this resolution with a single image, the image quality is really impressive. We use 128 channel coil for this specific acquisition developed by Russell. And here's an example of, I don't have the time, but I think here's about 35 minutes of data. And we can see that at this super high resolution, we can really preserve fine grain structure. And there's no smoothing, obviously there's Nordic here, but we can see that even voxels that are separated by a single line, they remain clearly separable and identifiable without blurring into one another, which is really, really promising. And with this, that's all I had to show you. I want to thank, obviously, all the people that worked and helped and provided guidance or active work on this project, especially Issa and Luca. And thank you very much.